I'm Rajesh Uppal, Director IDST. We bring sharp insights and foresight on defense, security, and emerging tech. Let's dive in.
Imagine walking into a factory of the future. Instead of rows of machines, one stamping metal, another soldering wires, another assembling parts, you see a single system. This machine doesn't just print the outer shell of a product, it weaves the circuits, the sensors, even the power source right into the structure itself. In one seamless process, the body and the brain of the device are born together. For years, 3D printing, also called additive manufacturing, has promised to change how we build things. Companies like HP and Stratasys showed us how to print complex shapes and combine different materials. But here's the catch. Those parts were dumb. They had no circuits, no ability to sense, no intelligence. To make them functional, you still needed to design and assemble separate circuit boards and wiring, which meant more time, more cost, and more complexity. That barrier is now crumbling. A new wave of technologies is merging structure and function into one process. Devices can come out of the printer already alive with intelligence, able to sense, compute, and communicate. And this shift isn't confined to one industry. It's pushing into defense, consumer products, aerospace, medicine, and beyond. Let's look at the pioneers bringing this vision to life. One of the earliest trailblazers is Nano Dimension. Their Dragonfly Pro system doesn't just 3D print plastics, it can also print conductive nano-silver inks alongside insulating polymers. That means it can create multi-layered printed circuit boards, antennas, or sensors directly inside a 3D object. No more etching copper, drilling holes, or painstaking assembly. You can literally print a complete circuit board inside a drone body or a satellite component. For defense, that's a game changer. Imagine a military base printing secure, custom electronics on site without waiting for supply chains or risking tampering. For aerospace, it opens the door to embedding electronics inside curved surfaces where traditional boards could never fit. Now compare that to voxelate, which takes a different path. Instead of making separate electronic boards, voxelate merges wiring and sensors directly into consumer products as they're built. Its printer combines ordinary thermoplastics, the stuff you find in footwear or wearables, with conductive inks for circuits. The result? Shoes with pressure sensors already inside. Sports gear that can track your movement without bulky add-ons. Even clothing that's born smart. Voxelate has already partnered with athletic brands to explore this, turning everyday items into intelligent products that blur the line between fashion and technology. And then there's the University of Missouri's free-form multi-material assembly process, arguably the most radical approach. Instead of adding conductive inks, their method uses a laser to transform parts of the printed plastic into laser-induced graphene. Graphene, for context, is a wonder material, 1 atom thick, stronger than steel, and an excellent conductor of electricity. By literally converting the surface of the plastic into graphene pathways, the printer can draw circuits, sensors, or antennas directly onto the structure. It's as if the material itself becomes the nervous system of the device. Afterward, additional coatings or semiconductors can be added to build even more advanced functionality. The inspiration here is almost biological, like how an electric eel's body acts as both muscle and power source. What makes these approaches so exciting isn't just their novelty, but the range of applications. In defense and aerospace, embedded electronics mean lighter, faster, and more secure systems. Airbus, for example, has explored embedding sensors in aircraft wings to monitor stress in real time. The U.S. Army has tested drones with circuits printed right into their bodies, ready to deploy within hours. In consumer products, Voxelate's technology makes wearables seamless. Imagine fitness apparel with built-in sensors that track muscle activity, or home appliances with circuits printed directly into their casing, eliminating wires and fragile connections. In healthcare, the University of Missouri's Graphene method is particularly promising. Implants could have sensors built directly into them, monitoring healing or delivering electrical stimulation without adding bulky external parts. Flexible medical patches could track hydration, body temperature, or movement without you even noticing they're there. But let's not pretend the road ahead is free of obstacles. Scaling these systems up to mass production is still a big challenge. Today, many of them are best suited for prototypes or small batches. Expanding the range of usable materials is another hurdle. Electronics often need materials that can handle heat, stress, or even survive inside the human body. Reliability is also critical. Printed circuits must last for years under harsh conditions. And of course, cost will determine how quickly small companies and labs can adopt these tools. Yet the direction is clear. Just as early 3D printing transformed prototyping, integrated 3D printing is transforming functionality. Instead of assembling separate components, we're moving toward devices that are born whole, structurally strong, electronically intelligent, and ready to interact with the world from the very first layer. This isn't just an upgrade in manufacturing, it's a shift in mindset. We're learning to design products the way nature designs living systems, where form and function are inseparable. And as these technologies mature, they won't just make existing devices better, they'll create entirely new categories of products we can barely imagine today. The future of manufacturing is not about parts, it's about systems printed in one go. A future where every object, from shoes to satellites, could be born smart. Thanks for watching. Subscribe, follow, or visit idsth.com for more cutting-edge defense and tech insights. See you in the next one.